In previous lectures, we discussed the expectation maximization algorithm for fitting mixture models. In this lecture, we're going to discuss Markov Chain Monte Carlo for Bayesian inference. In mixture models. So we're going to move from frequentist inference, in which we were interested only on finding the point estimate for the parameters in the model, to a situation in which we're going to try to explore a full posterior distribution for those parameters. So recall that the mixture model we are working with is going to take the form, or the density of that mixture model is going to take the form of f of x is the sum over k components of weights multiplied by the components in the mixture. And those components are indexed by this parameter theta k, and we may have components that all belong to the same family, or that they belong to different families. If we're going to do Bayesian inference for this model, we need to complement this density that is going to give us the likelihood with priors on the unknown parameters. And in particular, we're going to need priors for the weights, and we're going to need priors for the theta sub k's. And what is typically done in these situations is to use priors of convenience. And what are those priors of convenience? Well, first for the weights, remember that we have a constraint that the sum of the weights needs to be equal to 1. And obviously, each one of them individually needs to be between 0 and 1. So a natural prior for that type of parameters is a Dirichlet prior. And that is precisely what we're going to use. So we're going to assume that the prior for the vector that includes all these weights just follows a Dirichlet distribution with parameters a1 all the way to a sub k. And just as a quick reminder, the expected value of each one of these parameters individually is just given by the corresponding a divided by the sum of the a's. So in other words, the values of the a's just controls a priori what is the relative size of the different weights. And in particular, if you make them all the same, then you're saying that a priori you believe that all the weights are the same. And we also know that as a special case, if you make a1 equal to a2, all the way equal to ak, and in particular equal to 1, then we just have the uniform distribution on the simplex, which is actually one of the typical choices used for the hyperparameters when fitting mixture models. Now, this is our prior of convenience for the omegas, and we will see that in addition to having a very nice interpretation, it will also allow us to do computation in a very straightforward manner. Now, the other set of priors that we need is the priors for the theta k's. And what is typically done here is that if they admit a conjugate prior, under G sub k, then that prior is used. And the reason for that is that even though for the full mixture, this conjugate prior under G sub k won't be conjugate for the full model, it will be conditionally conjugate under our sampling scheme that we will derive in a minute. So it will make computation for the parameters theta k much simpler if we can find that conjugate prior under theta k. After we have set up priors for the model, the next thing that we need to do before deriving our Gibbs sampler is to write down the complete data likelihood in a slightly more convenient way. If you remember, the complete data likelihood that we used extensively for deriving the EM algorithm has the form of the distribution of the data and all those indicators C sub I that just tell you which component you belong to, conditional on the weights and all the thetas, is just going to take the form of a double product. So the product over the observations, followed by the product over the components of omega sub k, g sub k of x sub I given theta k raised to the indicator function of c sub I equals to k. In other words, rather than write the complete sum that we had before, we replace that complete sum by a product where each one of the terms is now raised to this indicator function that just depends on whether the component was generated, the observation was generated by the k component in the mixture. This complete data likelihood that we use extensively can now be rewritten in a couple of different ways. And one that is going to be particularly helpful for us involves breaking this expression into two pieces, one that has to do with the omegas and one that has to do with the g's. So let me start with the piece that starts with the g's. And the way in which I'm going to do it is first I'm going to reverse the order of these products. So I'm going to consider first the product over the components. And next I'm going to consider the product over the observations. But before I write the expression explicitly, let me interpret this expression up here a little bit. So what we're doing here with this double product, or one way to think about what we're doing with the double product, is to think about computing a bunch of terms that are in here, in particular in this piece, that can be positioned onto a matrix. Where one dimension corresponds to the index I, and the second dimension corresponds to the index k, and the entries of this matrix are just g of xi given theta k. So different combinations of I and different combinations of k give you the values that you are going to put into this matrix. Now, why is this important? Because if you think about what the indicator function up here is doing, it's just telling you, well, you need to compute the whole matrix, but you're actually not going to use the full matrix. You're just going to pick a few elements of it. And in particular, you're going to pick one element in each row according to what the value of C sub I is. So for example, if the first observation belongs to the second component, you would be picking this value. Second observation in the first component, you would pick this value. Third observation in the third component here, and so on. So the values of the C sub I can be interpreted as giving you a way to select elements in this matrix, and in particular one per row. So another way to write the product over all the observations is just to think about grouping rows together according to which column is being selected. And in particular, for example, we could put all the observations that have the first column being selected together, then all the observations that have the second column being selected together, and so on. One way to write that mathematically is to say that we're going to do a product over the i's, but group together according to the value of k. And then we can get rid of the indicator in the numerator and write this as g sub k, x sub I, given theta sub k. So this is one piece of this expression up here, or one way to rewrite this expression up here, or one piece of it, that involves the g sub k's. And of course, we have a second piece that involves the omegas. That second piece that involves the omegas, we can write as the product. Again, I'm going to consider the product over the k's first. And then for a given k, omega k is exactly the same argument for all of them. So I can just write omega k, and the product of omega k to the indicators just becomes omega k raised to the sum of the indicators. Well, once I have written the expression in this way, I can essentially think about this piece as being the distribution of the observations if I knew the indicators, the omegas, and the thetas. And it so happens that this expression in particular doesn't depend on the omegas. So for this model, this is the same as p of x given c and the thetas. And this expression here, you can interpret as the distribution of the c's given the omegas and the thetas. And again, in the particular structure of this model, this happens to just depend on the weights, omega. So we know that the product of these two quantities is just by the total law of probability, the expression that we wanted in the beginning, that it's the distribution of the data and the indicators together. So this particular form for the distribution is going to be particularly useful in terms of deriving the posterior distribution that we need for the Gibbs sampler. One last observation that I want to make that will be useful in the future is that if you think about what is the form of this piece down here, the distribution of the indicators given the weights, what you have is a form that resembles the kernel of a multinomial distribution. So this is similar to the kernel of a multinomial. And in particular, it's not only similar, but it's proportional to it. So it will be particularly useful in terms of deriving the algorithm using the fact that this looks like a multinomial distribution.